Good morning, everyone. Thanks for coming this early to my session. I hope it's going to be quite geeky with lots of numbers and charts and so on. And we're going to talk about serverless scalability today. But in order to warm you up a little bit, I want to do a quick poll. So if you can take your device and go to this URL, and if you don't have Wi-Fi, it's a serverless network, and the password is architecture, lowercase. So if you could go to this URL, you should see something like the poll will start soon. And if you are ready, could you please raise your hand so that I could see that? Or if you just don't want to take part, also raise your hand. Okay, still waiting. So I should be able to do this. It's the same URL, but this will show the progress if everything works. So, hands up. Okay, I think we had enough time. Anybody wants more time? Yes, I will start it right now. Yes. So let's start. There are several questions. And the first one, I'm using a serverless tech, you should say not really all the time. As you can see there, questions are not really nuanced. You always have to pick one of the two and just pick one that you feel like more. And then don't do compromises. Okay? So we have 25 people participating. Nice. 2/3 are more new to serverless than experienced. Next question. Serverless abstracts away the infrastructure. There is no need to learn the internals. Okay, so now 2/3 disagree, and that's probably why you came to this session, because you need to know more about the internals. That makes sense. Next question. Serverless functions are stateless. So it's always 2/3 and 1/3. Okay, mostly agree. We'll talk about this during the session. Next question. Serverless functions are either cheaper or more expensive but have benefits compared to processing the same workloads on the VM. I see. Yeah, the other is unfortunately cut out, but it has other benefits, advantages. Okay, no, not sure. 50-50. Next question. FaaS is an event-based programming model running on top of managed Kubernetes cluster or something like that. Okay, 2/3 don't trust in Kubernetes. Next question. Serverless can scale faster than any other tech that I know of. More skeptics. Okay. We'll see today. Yes. I think that's the final one, or maybe the last one before final. Cold starts, if you know what cold starts are, make serverless functions bad fit for many interactive scenarios. Okay. More believers that cold start is not a big issue. And yes, this is the final question. The more scalable your infrastructure gets, the better it is for our application. Yes, people want as much scale as they can get, which is fine. We'll talk about this during the slides. Okay, that's good. Thanks for participating. I hope you're warmed up a bit. So now, back to the presentation. So I'm going to talk about serverless scalability. First, I'll define in a couple of slides what serverless is for the purpose of this talk and what scalability is. So I'm going to talk only about function as a service today. Serverless is a big term, like it includes many services potentially, but I'm not only talking about FaaS today. And I'm also going to talk about the top 3 cloud providers, so AWS, Azure, and GCP. I will mention a couple of other vendors closer to the end, but these are the targets for my tests and analysis. Obviously, Lambda is probably the most popular one. I'm most familiar with Azure Functions, so I might be biased a bit. Just keep this in mind. And when I talk scalability, there are basically 2 parameters that I want to discuss. The first one is throughput. So the promise of FaaS is that you can develop your application, and then you can deploy it, and even if you have 1 user, it's going to work fine. But also, as your user base grows, as you get more and more users, you get to 1,000 or to 1,000,000. In theory, you should be able to use exactly the same application, and the cloud will take care of the infrastructure scaling for you. So that's the promise. And importantly, it's not just the sheer amount of users, but also the latency that you get from the service. Ideally, it should stay flat as the user base grows. It can be HTTP response time if you are using HTTP. It can be more broadly like how fast messages flow through your system if it's more async message-based data processing. But it should scale linearly and keep the latency under control. So these are the 2 parameters that I'm going to talk about mostly. And then, to me, there is a fundamental trade-off for the cloud providers. On the one side, they want to give the customer, the customer, the best value possible, like to serve in the best way in terms of performance, serve as many users as possible with as least latency as possible. But on the other side, you pay per usage, and they pay for their infrastructure. So on the other side, they want to minimize the amount of resources they have to spend on you while serving your workload. And that's always like in contrary. Ideally, from the customer perspective, you'll get the whole data center of AWS for your purpose forever, and they will serve your application. But that's not going to be very feasible in terms of the implementation, of course. And ideally, from the cloud provider perspective, they would not give you any infrastructure unless you get some load. And then they would only provision right at the moment when you need some load, the minimum amount of resources to handle your application. So I think overall, during my presentation, you will see how this balance is being found by cloud providers and where they differ from each other. So the plan for my presentation is to go through this scaling progression from 0 to 1,000,000 users and see what kind of problems you might get along the way. So let's start with just 1 user. We deployed our serverless application somewhere, and I'll have 1 example here. This is the basically GIF recorded from a web browser. So I created a simple map. Okay, it loads the tiles like Google Map, or that's rather OpenStreetMap. And the tiles are served from FaaS, from AWS or Azure Functions in this case. And then you deploy the application, nobody is using it, you send the link to your friend, and your friend opens the browser and goes to the URL. And that's what happens. Like, they start loading, the map is still empty because it's still loading. You see the timer going on the left. First tile appeared after 5 seconds. After 8 seconds, you get the full map. And then my friend, hypothetical friend, zoomed in a couple of times, and you see that the subsequent requests were much, much faster. Like the first load took 8 seconds. Let's look at this again. The first request took 8 seconds, or response rather, and then the subsequent requests were under 1 second. So probably you can guess that the reason for this is cold start. So every time you deploy the application, there is no instances ready to handle your load. When I send the first request to the server, the infrastructure and says, okay, do I have a worker to handle this? No, I don't. Then they go to the generic pool of workers, like they keep a hot standby pool of workers somewhere. They pick one, but then it's still generic, so it needs to download your code, it needs to run it, load all the modules, and then finally run your application code. So that's what happens during those 8 seconds in this example. Cloud providers are obviously smart enough to keep those workers alive for some time after the first load. So the second load will be a warm start, because now they will check, okay, do I have a worker for this load? Yes, I do have one. They will pick one, and then they don't need to do anything else except just running the code. So it's going to be much faster. So several questions here for how long do they keep the worker, and then how bad are the cold starts for your latency. And I'm going to show you a couple of charts about this. So I start with the interval. So that's for Azure, and this chart shows some sample requests. The vertical axis is duration, and the horizontal axis is time interval between two requests, subsequent requests, in minutes. So for Azure, you can see the clear picture that after 20 or 21 minutes, they kill your worker, and if you hit application at that point, they will have to go for the cold start. And all the points before that, they are always fast. Now, for AWS, the same chart, but it's a bit less deterministic, let's say, because they always keep the worker for 26 minutes, I believe. And then there is some probability that they will kill it. And they can sometimes keep it up to 1 hour, or even a little bit more. But the longer you have no requests, the longer it takes, the higher the chances are that you will lose your worker and have to hit a cold start. This is not really documented. I think they say like 5 minutes is guaranteed, but in practice it's more. For GCP, it's even more random-ish. So they can kill your worker after 3 or 5 minutes, or they can keep it for an hour, or even I saw live workers after 5 or 6 hours sometimes. It's not on this chart, but they can keep it for quite long. So what happens here, probably they have like a demand-supply evaluation. If there are a lot of applications usage in the data center and then they lack those generic workers, they start to garbage collect your instances. And if they have enough spare capacity, they just keep it for as long as they can without it bothering. So the next question, how slow are cold starts? And this chart is trying to answer this. So the vertical axis now is the second it takes for a hello world type application, very lightweight application, to load for a cloud provider and language combination. So you can see that AWS is probably ahead of others, except for .NET Worker, to some reason. And the bold color is the most probable range. Like 2/3 of your request will end up in this colorful bar, and the bigger bar is like 98% of requests. Okay? So you see that almost all AWS requests for hello world functions again will complete within 1 second. GCP is like 2 seconds. Azure.NET is sort of fast but has a long tail. I think they have 2 scenarios, like one when you are lucky, one you are not lucky, and then sometimes you hit those 8 kind of seconds. JavaScript for Azure is quite slowish here, as is AWS for .NET. But that's hello world, because they just need to download several kilobytes of your code. If you start creating bigger applications, you have more dependencies, you have more modules, NPM modules, Maven packages, NuGet packages, whatever. The cold start will start to grow. So this is an illustration of this. These bars are for free types of applications. Hello World is a green one, and then you have 5 megabytes of dependencies and 35 megabytes of dependencies. And you can see that it grows quite substantially. Azure is quite slow because it's JavaScript. .NET will be faster, but still. Even AWS is like 3-5 seconds for a big application. And GCP 7, 8-ish. So the first question that they asked, like, if cold starts might be a blocker for interactive applications. Yes, probably they can be. They are getting better all the time. They are working hard to reduce them, but still several seconds can be very frustrating for some scenarios. You have to realize that only a small portion of your real-world requests will hit a cold start. So if your application is sort of very live, it's not that often that you will see this, but it will happen, and it happens not only for the first worker, but even when cloud provider wants to scale out, so create a second instance, third instance, 10th instance, all of those will be cold starts. So at any scale out, you will hit some increased latency. And you should be prepared for this. Now there are some workarounds to minimize cold starts. Here is an example for Azure. Because you can put multiple functions in the same deployment unit, you can hack it a little bit and create a timer-based function which will run every 15 minutes. And this will prevent the first instance from being killed. It might still be killed after several hours, like when they need to move you to a different part of the data center or something. But usually it will survive several days without being garbage collected. You cannot do much to keep second, or third, or 10th instance alive, because this will run only once. On an AWS, you cannot put multiple lambdas in one lambda. Well, that's just your deployment unit. So you can define a cloud watch event for the lambda, but then you also have to change the code of your lambda so that when cloud watch event triggers, you just short circuit and quit immediately so that you don't spend too much time and don't pay money for this. Like, people often ask if this kind of defeats the purpose and now you pay for full-time utilization of your lambda. No, because you only pay for 100 milliseconds once in 10 minutes or so. So that's going to be very cheap, actually. You will not notice this. I'm also curious why cloud providers themselves wouldn't do this. Like, if it's relatively easy to keep one instance alive, they could just make it a feature, a flag somewhere, but maybe they don't want you to do this. Now, if you want to keep multiple instances alive, you have to do much more sophisticated tricks. So there is a post by Jeremy Daly. Jeremy somewhere here in the conference, ask him. You can have like Cloud Watch event and then a special lambda which would trigger multiple parallel requests to your target lambda. So that if you do it every 10 minutes or so, you run 10 parallel requests that should ensure that you always have 10 instances running for your application. So if you can predict the maximum parallelization of your lambda, you kind of work around the cold starts. But again, don't do this unless you need to. Maybe a lot of applications don't really care about cold start that much. Okay, enough about cold starts. Let's say we grow, we have now 100 users, and now it's time to learn how actually serverless applications or serverless environment infrastructure works behind the scenes. So let's spend some time digging into this. First question is, what is the deployment unit for your application? It could be like a physical server, which is unlikely. Then it could be a VM. It could be a container inside the VM. It could be a process inside the container inside the VM. Or they could deploy multiple functions inside the same process as just tasks or threads or something like that. So first let's make this clear, like what's the Kubernetes usage chart for major cloud providers? And the answer is none of them do use Kubernetes, right? I think like the smaller ones maybe do. So that's another myth that I've heard before. But then there are two questions. The first one is the tenant isolation. So I'm deploying my application, you're deploying your applications. can they run on the same hardware? Can they run on the same VM? Can they run on the same container maybe? So it's the answer is not obvious, but sort of all three cloud providers came to the same answer, that the isolation unit for tenants is virtual machine. If you start putting multiple tenants on the same virtual machine, you get nasty security issues when some noisy neighbor can probably do something like writing a lot of disk data and sort of attack your functions. So if you are just starting with a FaaS and you deploy your first function, you will always get your own VM where your code runs. You will not share it with anyone else. And then if you start deploying multiple functions or multiple instances of the same function, then the answer differs. So Amazon and Google will start deploying multiple instances on the same VM in different containers. Every container will get a slice of resources like CPU, memory, but they will share, for example, disk of the same VM. Azure is a little bit different because they have two answers here. One is that you can put multiple functions in the same application, what they call it, and then those functions will always be deployed together in the same VM, in the same process actually. Or alternatively, you can create multiple applications and then they will not share even VMs. They will just be on a separate VM always. So there is no container store in Azure. Let's understand a little bit more about how concurrent executions or instances are packed. So AWS and GCP again are very similar. The first instance will hit a new VM, the first execution, let's say. So you run your function once. And now if you run it multiple times concurrently at the same time, they will create multiple containers and will bin pack your VM, so they will put as much as possible of those containers on one VM. And when that one is full, depending on how much CPU and RAM you provisioned, they will start a new VM and then will pack that VM with containers, and so on and so forth. And every container is synonymous to one concurrent execution. So one container will never run multiple executions at the same time. Even if you just have a timer and then pause for a second, this resource is fully dedicated for that execution. So you kind of get the predictability of the resource pool, but also the utilization might not be optimal in case of I/O heavy things. And if you're just waiting for a remote web service to answer, your instance is effectively idle. So in this example here, I have 3 concurrent executions, at least they overlap. Each one takes 1 second to execute. So here you can see that the AWS GCP side of things will provision 3 executions for you, 3 hosts. And you will also pay separately for each one of those. You will pay 1 second for A, 1 second for B, 1 second for C. Now, if the next execution comes in later, they will reuse these instances, of course, but they will never overlap those executions. For Azure, it's a bit different, as I said. They will deploy a function app into VM, and then they can also run multiple executions on the same VM at the same time. There are some knobs and ways to configure how many executions you want to be run in parallel, and this also depends on the trigger type. But that's a bit of a mix of their decision and your decision. So you cannot really control this with high granularity. And the idea of theirs is that most applications are not CPU bound, they are IO bound. So if you pack multiple executions on the same instance, you get better resource utilization. Remember the trade-off that I discussed. And you also get benefits from this, because if you have 3 executions, as in last example, and they are put on the same host, you will only pay for, so let's say 1 execution. So you will pay for 1.5 seconds here in total. So it's going to be 2 times cheaper than AWS in this example. But they can also start competing for the same resources. So if you are doing some CPU intensive work, they all will get slower eventually. So for the concurrency, the trade-off is isolation and predictability versus price in resource pooling. And this provider has different answer for this trade-off. Okay. Now we learned this model. Let's grow further. Let's say we have 10K users, and we might get some problems at this point. Let's discuss the problems by an example. So that's like a typical serverless applications. You have some upstream components like user interface which calls your function, or a queue with the messages, and so on. And then you probably have some downstream components because your FaaS is just stateless function. So you probably need to read some data from database or call some third-party web service or a web service from your other team, which is not serverless. So let's spend some time looking at the right part of the equation. So downstream dependencies of your applications. In more traditional setup, let's say you had a couple virtual machines where your JVM application web service would run and then would call third-party services and databases. So those VMs would typically live for days, and they can utilize this fact to keep, for example, a pool of TCP connections and to keep DNS cache or some other pooled resources. And the load on the web service will not change that drastically over time. Like you might get more users from time to time, but it's just 2 or 3 VMs, so you know the upper bound of the load on the dependencies. Same goes for SQL database. Creating a new SQL connection is very expensive, so usually you just have multiple connections in the pool, and then multiple threads share this pool of connections to call database, and that's quite efficient, and that's how the protocols for SQL databases were designed in the first place. Now, in the new great world of FaaS, you don't know how many instances you're running on the left side. It can be 1, it can be 100, it can be several hundreds. And also, they are short-lived, so they might be created and killed. So all those ideas of pooling and so on, they are questionable. Like, can I do the same technique? Can I apply the same technique to the new world of serverless? On top of that, you also might get too many executions created at the same time, and then you might hit hard your web service or your database. So let's say you got scaled up to 500 instances, and then they all try to connect to your SQL database. And then the requests, the queries start getting slower, and you get more instances, and they all try to connect to the database, and it's overloaded, and basically you are DDoSing your own infrastructure. So my answer to the question of more scale is always better. It's not always true. Like if you are using some dependencies which are not serverless and dynamically scalable, you probably at some point want to limit the scalability in order to limit the impact on your infrastructure, and don't shoot yourself in the foot. There are several ways to do this. It depends a little bit on the trigger type, so what's the event for your function. The best case scenario is that you are using something like Kinesis or Azure Event Hubs, where the trigger itself is partitioned, and then you know that you will never get more executions than partitions on the trigger. So one execution is always handling just one partition. So if you have 4 partitions, you only get 4 concurrent executions. So that's a natural way to limit your scale-up boundary. If you are not that lucky, or if you did not design your code in this manner, there are some knobs. For example, in AWS, you can reserve concurrency for your Lambda. And it's not just reserve concurrency, but it also plays as a maximum concurrency if you read the docs. So if you say it's 10, AWS will make sure that you never get more than 10, and if you start hitting harder, like get more HTTP requests, they will just be bounced off. So that's it has pros and cons, but if you really want to make sure that your database is always up, you can set this to a value which makes sense and be sure it doesn't scale up further. For Azure, there is also a similar setting, but it says that it's in preview and only works for values below 5, I think. So they are working on this, but it doesn't work reliably yet. But it's the same idea. Limit the maximum scale out to a value that you specify. So to the second problem of pulling the connections, TCP connections and SQL connections. You can still do this, and you actually should do this, because instances are not really short-lived. Your executions are short-lived, but as I said, as I already explained, the instances themselves will be reused between requests. You should understand this, and you can keep the pool of connections in the instance, hoping that it will hit another execution pretty soon. So you should do things like this. Keep alive TCP connections. If you are on Azure side, you do Azure functions, or actually if you're just writing C# code, you should use something like static HTTP client and not create it for every execution separately, which is a common mistake. For SQL, this works the same way. If you just keep using your normal C# Java connection pools, they should work. But it gets more tricky. Another reference to Jeremy Daly here. He created a library and a blog post of how you can best utilize your MySQL database in the reality of AWS Lambda functions. So just my message here is spend some time on analyzing what kind of issues you might get with connection pooling, what's your scalability model is, and just apply some best practices. To this regard, I should also say that, in my opinion, serverless is not really stateless. You can keep cache of connections, pools. You can also cache some data. That will survive between requests. There is just no guarantee, and also there is no guarantee which exact instance will handle your next request. But at least you should utilize these practices in order to make this efficient. Okay, finally get into high scale. So I ran several performance tests, which I want to share with you today. And the first one goes to more asynchronous data processing scenario. So let's say you have something like a queue, SQS or storage queue or PubSub, and then your serverless function is bound to that queue, and it does some useful information, usually puts some data into database or reads some data in database, calculates something and so on. So that's the scenario. And then I ran a couple of tests. I did not use the real database to make this more reproducible, so I have two types of functions. One is sort of I/O bound, it just waits for half a second and then quits. So it's not really doing any CPU intensive work. And the second one is gonna be CPU bound. It's just calculating bcrypt hashes, which is very CPU intensive task. And then I run both of those tests on all three cloud providers. So the test looks like this. I shoot 100,000 messages into the queue, and then I measure how long it takes to process all of them. And ideally, again, in your ideal world, Lambda could, or Azure could just spin up 100,000 instances. Each one will take one message, and this will be like super fast, except for cold start. But in several seconds, you will get your data processed. But this is not realistic. Like they're not gonna spin up 100,000 instances just for your queue. So the question is what is the exact behavior? The first test is for waiting function, so lightweight one. This is a chart for AWS. So it starts on the left with 100,000 messages. The yellow line goes down. That's how many messages are left in the queue after some time. And you see that it takes 5.5 minutes to process all the messages in the queue. And the bars here show how many instances you get from AWS. So at the peak, at the end, we have 300 something instances. And that's actually a well-documented behavior for SQS. At least they say that they will add 60 instances per minute or 1 per second for you. So the longer your queue is busy, the more instances they will start adding 1 per second. Okay, and you see that the real behavior is pretty close to that documented scalability. Now the same chart goes for GCP. So the red line instead yellow, for the rest it's the same. It took a little bit less than 5 minutes, so comparable, but you can see that the scaling behavior is very different. It took like half a minute before Google realized what's going on, and then they just jumped to 300 instances immediately and kept them more or less flat for the rest of 4 minutes. So my guess is there is no documentation about this. They don't explain how they would do this. But my guess is that they just looked at the queue, how many messages there are, some maybe data about the first 30 seconds of how the processing goes, and then calculated approximately how much instances they need, and then balance this with the amount they have. So we got 300. Now the same chart for Azure. It looks very much similar to AWS, the chart itself, but if you look at the right side, you will see that they only provision 20 instances or so. So like order of magnitude less. And that's because they pack executions quite aggressively on the same instance. So same instance is doing multiple executions. And because executions are very lightweight, they don't interfere with each other. So it's quite efficient to process these messages relatively fast, even with this small amount of resources. And 10 times less instances means also 10 times less money, mostly, because you pay per active time of each instance. So if your workload is very I/O bound, you can get a lot of benefit from this packing on the same instance. Now I want to explain a little bit about how scaling works for all free providers. So these are my pictures, my understanding of how it works. Some of this is documented, some not. So take it with a grain of salt. But again, AWS versus Azure have slightly different models. So in case of AWS, the queue is on the left side, and then there is some central party which is hidden from you. It's fully managed by AWS. I called it controller. I don't know the official name. But that's the one who knows about SQS. It can read messages from the queue and then distribute them among workers, among the active workers. And it's also the one deciding how many workers it needs. So it pulls all the messages and shoots one by one to workers, watches which one is busy, which one is not, and then distributes the load. It also has the full power of scaling, so it knows how to decide the scale. And the instances are sort of dumb. They just get one request, or one response, one request, one response, and so on. In case of Azure, it's a bit different. So every instance is much more powerful. They know themselves how to connect to the data source and pull the messages. So every instance on their own will pull messages directly from the queue. And the powerful party, which is officially called scale controller, its role is a bit different. So it gets the telemetry from the queue, how many messages are there, how fast are they going. It gets also telemetry from the workers, but it doesn't directly distribute the messages between the workers. So it's a bit more nuanced, and I can imagine it's a bit more difficult to adjust scale that precisely, because it doesn't really manage the messages themselves. It just creates instances and kills instances. And then instances themselves are in charge of pulling messages and committing them. So that might be another source of difference in the scalability. Now the second chart go. This time, to remind, I have very CPU intensive workload, which takes like a second of computation, fully busy CPU. So that's the chart on AWS. Again, 100,000 messages thrown, and then it scales up. This time it took almost 10 minutes because it's just 2 times slower, I believe. But you see the scaling pattern is still exactly the same. They add 1 instance per second, and it grows up to 600 instances at the end of the test. And the curve is still pretty perfectly quadratic, like it's a parabola going down. Same chart for GCP. You can see the same behavior, like 30 seconds in the work. They spin up 300 instances, about-ish. And then also sometimes afterwards, they also add more instances, and so on. So they actually complete much faster than AWS in this case. Well, 6 minutes versus 10. Of course, this might differ per workload, so this is not really representative, but it should give you an idea of the behavior. And you see that in the end, we have almost 1,200 instances working on the same application. So when was it the last time when you provisioned 1,200 VMs in your application? You really didn't need to do much here in order to do this. And now the same chart for Azure, and you see that it took more than 20 minutes this time. And that's the downside of the model that they use, because they pack a lot of executions on the same instance. And now they don't get any benefits from that because it's purely CPU bound. They just compete for the same CPU, and they were not able to adjust to this workload that efficiently. So they only provision 50-something instances, and you don't get any price benefit in this case. You just get longer executions. So probably this scaling model is more suitable for IO-bound workloads than CPU-bound. Again, there are some knobs, so you could limit the maximum amount of executions to the same instance, but it doesn't get you that far. Another important aspect for AWS and GCP is that you can provision different amount of memory to your instance. So you can start with 128 max, or you can go up to like 3 gigs or 4 gigs, I don't remember. And the not very intuitive part of this is that the CPU share that you get is proportional to the memory. So even if you don't need a memory, but you need a CPU, you probably should provision more memory to your function and then get more CPU cycles. So in this example, it's the same test. I ran it 2 times, one for 128, one for 512. And you can see that 500 megs is perfectly 2 times faster than 128. Actually, it's 4 times faster, but because it's quadratic, it completes in 2 times faster. So that's quite reliable if you want to run CPU-bound workloads, even if you don't need a lot of memory. Try provisioning larger instances, and then you get a fair share of CPU, and your executions will be shorter. You will pay more, so you will not save any money on this. They will cost almost exactly the same because they charge per memory times execution time. But at least for the same buck, you will get better performance, so it makes sense in many cases. The conclusion here is that serverless is not really a magic box. You still need to understand a little bit about the concurrency model, a little bit about scaling behavior. You should probably run tests for your workload to see how they fit with the current setup. And also you should have some idea about the resource model, like RAM provisioning versus CPU allocation and so on. So it works pretty great. You saw the 1,000 instances example. But you still need to understand how it works behind the scenes to optimize that. So my final chapter is going to be the HTTP test. The idea that I had is that I want to try to serve something like Stack Overflow scale of traffic. Stack Overflow is a good example. Well, first, everybody knows Stack Overflow. And second, they are very public about their data, so they have all the statistics about how much traffic they have, how big the pages are, what kind of tech they use, and so on. Of course, I created a very, very simplified version of Stack Overflow. I'm serving the traffic of question pages. The traffic should be realistic, like I take the real HTML, and then I saved like 10,000 questions to my database on blob storage. And whenever a request comes in, I load HTML template, I load JSON data of a question, and then I put JSON data into HTML and serve HTML back to the user. And so it involves IOs for accessing blob storage 2 times, well, 1 time, HTML is cached. And then it involves serving traffic to the end browser. And then the public figures of a couple of years ago of Stack Overflow said that they get about 1,000 requests per second to the site. So quite a decent load, probably not, definitely not like Facebook or something like that, but quite a big load. So I came up with this scenario which peaks at 1,000 requests per second. This is amount of requests per second over time. And the scenario is like 20 minutes, or I only show 17 minutes here. I guess I cut the zeros here. So this is the load test. I ran it on all 3 providers. And then I show the percentiles of requests. If you don't know what percentile is, 95 percentile means that 95% of requests were faster than this value, and 5% were slower than this value. Okay. So first start with Azure functions. I'll help you read this. So the horizontal axis is minutes again. The faded away bars is requests per second, just for your information. And then the lines have different percentiles, and the left axis, vertical axis, is milliseconds. So it gets up to 3 seconds in this chart. So you can see that first 50 percentile median is very fast. It's somewhere like 15 milliseconds. So on average, sort of, users get very fast experience. But even the 95, so 5% of users are experiencing sometimes the delay. Especially on minute 4, something happened. Not sure what. And then around the middle, but also somewhere in the end a little bit. And the same chart, but 99th percentile, so the unlucky 1% of users will be slower than this, like 8 seconds now. I suspect there are some cold starts in here, because it's just 1% now and then it scales out, but probably not all of them are cold starts. So it does get slower to several seconds, but still 1,000 requests per second with pretty steep growth. The results are quite okay to me. This chart shows the number of instances, so the ones we talked before with the queues. They scaled up rapidly on the 4th minute. You remember the spike there in the latency. So those were probably cold starts included. And then it kind of flattens out. And just not that many instances actually, just about 20. Now, comparing to Google functions. This one is almost perfectly flat, 95 percentile. Goes up to 600 milliseconds. But notice that actually the 50th percentile is quite slower. And that's because just the blob storage of Google, for my request at least, appeared to be much slower than Azure's blob storage. I'm not sure why, but that's the effect of the downstream dependency, not the functions themselves. Functions are quite responsive. There was just one small glitch. 99 is a bit more rock and roll in the first part, but it's still about 1 second, so nothing dramatic. You will not notice a lot of delay here. So this is quite cool. Instance-wise, they provision more instances than Azure again, because just instance is a smaller thing. It's one concurrent execution. And I'm not sure why it goes a bit up and down and like this, but that's what I measured. And then after the peak, you can see that they still keep a lot of instances alive and distribute requests between them evenly, even though they probably don't need this amount of instances anymore, but they expect more load because my scenario is sort of artificial. So they expect more load. If your load is not that spiky, you will get a lot of cached instances and even less problems. Now finally, the data for Lambda. 50 percentile is almost as fast as Azure. Again, S3 is a bit slower than Azure storage for my scenario. But the rest is just plain flat, like Lambda did not seem to notice your or my increase in the traffic. They just fine serving it all at about 100 something milliseconds. The 99th is also flat, spiked just once. I don't know. So it still might spike sometimes, but for the rest it's dead flat, and they are fine with your 1,000 requests per second. And actually it's not that high of a load. They just use 80 instances behind the scenes. So it's, I guess I could try to scale to like 10,000 requests per second and still be okay, because the queue scenario provisioned much more instances for my workload. So the question of scalability, in my opinion, the service is very scalable. I never dealt with infrastructure which could scale to something like this in my past. Maybe some of you do, but I think the sheer scale is probably reachable with many other techs, but the rapid scale out from 0 to hero, that's quite unique for serverless. So wrapping up my presentation, yes, 5 minutes, perfect. You saw some problems still, so instead of just repeating this thing again and again, I want to show you a couple of different tech which might be influencing our future, our serverless future. So on last reInvent, Amazon presented something called AWS Firecracker, and that's a very lightweight virtual machine which can start in 100 milliseconds, and it consumes just 5 megabytes of RAM for itself, like before your load. So it's super efficient. They plan or already use it for Lambda and Fargate. I think it's partially, and then they can pack thousands of those VMs into one physical server. And at first it might seem like a solution to cold start problem because it can boot so fast, but actually VMs that you get at cold start, they are not booting when you request the service. They are already booted and prepared for you. Everything is cached and so on. But this might be important for Amazon themselves actually, because they can pack much more VMs on the same hardware, so they can get much higher utilization of CPU and RAM, and then hopefully, if we are lucky, transfer some benefits in terms of price or scalability behavior. So that's more, they made a lot of noise around it, but it's more of their advantage than ours, in my opinion. Then I'm familiar with a startup called Binaries, I'm still not sure, different people pronounce it different. It's a startup, they only do FaaS, they don't do anything else. And they actually run their functions on top of AWS. But what's interesting here, why I've shown them, they claim that there are no cold starts. They are smart enough to pre-provision instances for you and keep something in the pool so that you never hit cold start. Well, of course, with some SLA 99% or something like this. They cannot always guarantee this. And they are extremely fast to scale out. So compared to AWS even, they claim they are much faster, and they target workloads where you need to do massive parallel compute, like calculations on graphs and so on, on FaaS. So that's interesting, at least the idea to compete with major cloud providers by using their infrastructure but being more efficient is quite ambitious, so I thought it's worth mentioning them. Now, Cloudflare, probably most of you know Cloudflare. They are like DNS kind of service, mainly known for this. But they have an offer called Cloudflare Workers. And this is JavaScript FaaS, but they have very different compromises that they made there, trade-offs. So instead of using VMs for your functions, they use something called V8 isolate. So basically they run your workload inside the Chrome engine, JavaScript engine. And because it's so lightweight, they can pack thousands and thousands of functions on the same machine. So what they actually do is quite mind-blowing. Every time you deploy your function to their infrastructure, they deploy it to all servers of Cloudflare which serve workers everywhere within 5 seconds. So they have like 150 points of presence around the world. They deploy it everywhere. And then when you call the worker, you call the function, you will just hit the closest to you server somewhere in the neighborhood. And the response can be very, very fast, so like CDN-like fast. Of course, there are many limitations that you can do, that you cannot do. Some people question the security model of V8 isolates, but actually V8 is running in every browser, on every machine in the world, so security should be quite okay at this point, because multiple sites could then interfere with each other if it's not. So that's an example of different trade-off that the cloud provider is making, and I'm curious to see where they end up with. So I gave a lot of charts and data. If you want to read more of this, I have several blog posts. The slides will be online just after my presentation, so you can navigate to those links and go for the same material or comparable material at your own pace. Yes, everyone mind the picture? Okay. And with this, thank you for listening, and enjoy the rest of your day.